Welcome to lecture number 11 of mechatronics. We are going to see in this lecture My name is Sachin Todkar, Assistant Professor, Mechanical Engineering Department, Navachai Year 3. We are going to see in this lecture time domain and frequency domain analysis of the system. Now, we have seen one numerical based on stability of the system. Now, how the stability has been established, we are going to see here. So, if your roots of equations are lying on the left side, then we can consider it as asymptotically stable system. In this, each of the poles of the transfer function are strictly in the left half plane. That is negative real part of that system. Here you can see in graph the sigma. This is a real axis and j omega is your imaginary axis. Now one or more pole lie on the imaginary axis, and all these poles are distinct. Then it is marginally stable system we can call. In case of unstable system, at least one pole lie in the right half of the plane and has a real part greater than 0, that is positive. Then it is called as a unstable system. Now, after deriving mathematical models of the system, we can done its analysis with the help of time domain and frequency domain. This basis may be set up by specifying particular test input signals by comparing the responses of various systems to the signal. Normally, following standard input signals are used to identify the system performances. We are going to see in detail these: step function, ramp function, impulse function, parabolic function, and sinusoidal function. Now, what is time response analysis? Time response analysis is the plot that describes the behavior of the system and contains much information about it with respect to time response specification, and contain more information about it with respect to time response specification as overshooting, settling time, peak time, rise time, and steady state error. All these terminologies are very important. We are going to see in the next slides that we have to see their definitions and how they have been derived. Now, classification of time response. When the system gets started, there will be a transient response of that particular system, and after some time it will become steady. So there will be transient response and steady state response. Now, what is transient response? As the name suggests, transient response of the control system means change in the system. It occurs mainly after two conditions, and these two conditions are written as follows. Condition 1, just after switching on the system, that is at the time of application of an input signal to the system. And second condition, just after any abnormal condition, that is if there is any sudden change in load or short circuiting, etc. Now, what is steady state response? Steady state occurs after the system becomes settled and at the steady system starts working normally. In that case, it will start working normally. It will be, or you can say, soothed. Steady state response of the control system is function of input signal, and it is also known as forced response. Now we will see one by one standard input signals. Now, first signal, that is called as step signal. If you can see in the diagram, there is a step input here, 0 to A, and it is in steady state now. The step signal defines the sudden change in properties of actual signal. It is being used to see the transient response of the system, as it gives you the idea about how the system reply to interruption and somehow the system stability. Okay, so the equation will be u function of t is equal to a when t is equal to or greater than 0, and it is 0 when t is less than 0. Means when time starts from 0 to anything, it will give the output a. When a is equal to 1, then the step is called as unit step signal. Examples: if the input is an angular position of mechanical shaft, a step input represents the sudden rotation of the shaft. Switching on a constant voltage in an electrical circuit will represent a unit step signal. Again, third, that is sudden opening or closing of valve will give you step signal or unit step input signal. So these are examples of step signal. Now we'll see second one, that is a ramp signal. The ramp signal tells you the constant velocity attribute of actual input signal. It is being used to determine the behavior of system with velocity factor. When a is equal to 1, ramp signal is called as unit ramp signal. Now here you will see the function as a into t. For ramp signal it is r function of t is equal to a into t or 0. Example is altitude control of an missile. So if you want to control altitude of a missile, it should be function of time, and you'll get this type of graph in ramp signal. Now third one, that is parabolic signal. Parabolic signal gives a constant acceleration distinction of actual input signal. It gives the idea about how the system will respond along with acceleration. So in this case, you will see for parabolic signal, the function is pt, and it's a t square divided by 2. It is a equation of parabola. So when a is equal to 1, the parabolic signal is called as unit parabolic signal. So in this case, this parabolic signal will be function of time square divided by 2, and it is a function of we can see that it is equation of parabola, so it will behave like a parabolic signal. The fourth one, that is impulse signal. In this case, impulse signal is delta t is equal to a or 0. Impulse response in control system initiates sudden shock quality of actual input signal. Impulse is the output of system when given by small input. Impulse responses emphasis on change in the system in reaction to some external change. It is a reply of the system to the direct delta input. When a is equal to 1, then impulse signal is called as unit impulse signal. This impulse signal will be seen like this, or we can see on, you can say the wave as an impulse generated here. Example is a sudden shock, that is high voltage due to lightning or short circuit. So that is called as impulse signal. Transient response specifications. We are going to see what are these terminologies. That is delay time. Here you can say TD is delay time. TR is rise time. So it is a rising time. Peak time, maximum overshoot, and settling time, TS. So they have shown here TD, TR, TP, TS, MP, and these are some terminologies in transient response. Now, what is delay time? This time is represented by TD, the time required by the response to reach 50% of the final value of the first time. This time is known as delay time. Delay time is clearly shown in the time response specification curve with the help of this TD. You can see here 0.5, that is 50% of rise. It is giving TD or delay time. Rise time, here is a time required for the response to rise from 10% to 90%, 5% to 95%, or 0% to 100% of its final value. For underdamped second order system, 0 to 100% rise time is normally used. For overdamped system, 10% to 19% rise time is common. Now there is one expression for the rise time. We have to equate the expression of Ct equal to 1 from the this above equation. We have it is e raised to minus eta omega t sine in bracket omega under root 1 minus eta square d plus tan inverse of under root 1 minus eta square divided by eta whole divided by under root 1 minus eta square. So this is the equation for the rise time. Solving above equation, we have the expression for rise time equal to TR is equal to this pi minus tan inverse under root 1 minus eta square divided by eta whole divided by omega 1 minus eta square. So we'll see in detail what is omega n. Omega is natural frequency of vibration, and if we'll put these values, you'll get the simplification of that particular value. A peak time, all this have in peak time is represented by TP, the time required by the response to reach the peak value for the first time. This time is known as peak time. Peak time is clearly shown in the time response specification curve. We are not going to go in details of these formulas right now. We'll see in details in next lecture. Settling time, the time is represented by TS, the time required by the response to reach and within the specified range of about 2% to 5% of its final value for the first time. This time is known as settling time. Settling time is clearly shown in the time response specification curve. You'll see it again. Here, TS is a settling time. So it is 0.02% of that particular allowable tolerance limit. Maximum overshoot, it is expressed in general in percent of the steady state value, and it is defined as maximum positive deviation of the response from its desired value. Your desired value is steady state value. So again, we'll see the maximum overshoot here. Desired value is 1 here, and maximum overshoot is here MP, which has been shown in the diagram. So these are the terminologies about all these things. Steady state error. The steady state error is difference between the actual output and the desired output. Hence, at the time tending to infinity, the steady state error is 0. System, second order system and transient response specification. Now we know in last lecture we have seen spring mass damper system with small excitation of X. We know the formula for that, and if we'll use a Laplace transform, you'll get the simplification like this. So this YS will be simplified with the help of all the terminology, and you'll get the equation like this. This is the derivation how natural frequency can be calculated. The natural frequency is nothing but it is the spring constant divided by mass, under root of spring constant divided by mass. Eta is equal to B divided by 2 under root K into M. And if we use these values for calculating, you'll get value of S1 and S2. You can find out these values and you can predict the system is stable or not. This is a unit step response curve for second order system. You will see how the eta will change the response of the systems. If the eta is 0.2, you will see there is maximum overshoot. If it is 0.5, it is less. 0.7, it is very less. 1, it is very, you can say, stable. If it is over damped, then again you will see some. By if over damped by 2 or 5, you will get a different kind of curves. So damping factor will help you deciding the steady state response of the system. These are some useful formulas for step response specification of second order model. How you are going to define that second order model's stability with the help of transient response specification. So these are the roots how you can calculate. Damping ratio, how you can calculate here. Undamped natural frequency you can calculate. Damped natural frequency. These things are important in your syllabus. These are some formulas, additional formulas here. And this is frequency response analysis. By the term frequency response, we mean the steady state response of the system to sinusoidal input. In frequency response methods, we vary the frequency of the input signal over a certain range and study the resulting response. The steady state output of transfer function system can be obtained directly from the sinusoidal transfer function. That is the transfer function in which S is replaced by J omega or I omega, where omega is frequency. So in this case, we are going to change your time domain to frequency domain. If input xt is a sinusoidal signal, the steady state output will also be a sinusoidal signal for the same frequency, but with possibly different magnitude and phase angle. So these are some formulas for defining frequency response analysis. In next lecture, we'll see some detailed numericals based on frequency response and time response analysis. So if you have any questions, you can ask me right now, or you can pose the questions, and we'll discuss these questions in next lecture. We'll meet again in next lecture. Till then, Sachit Dorgal signing out. Thank you very much.